first presentation will be titled as Model Predictive Control for Soft-Growing Vine-like Robots. I'm Haytham Hussein. I'm a Senior Research Fellow in Soft Robotics at the University of Salford in the UK, United Kingdom. So to start directly, currently we have a trend in robotics called soft robotics, and these robots are structures or designs that are flexible and compliant, that are bio-inspired by maybe the snakes or elephant trunks and octopus tentacles as well. They are flexible. They can they are safe for human. This is the main feature. They could maneuver in tight spaces and in restricted environments as well. And finally, they are having a low cost compared to rigid robots. But the issue here with continuum robots or continuum flexible robots, that they have small lengths, and this is the issue. We cannot use these kind of robots to go through distant environments, or we cannot explore a distant environment. So that's why currently we are talking about growing robots. These are robots that are flexible as the soft robots, but they have the ability to grow inside the environment. Like if we need to inspect a pipe or something, so we can grow this robot, this growing robot. It is like inspired by plant, so it will grow inside the environment too. We can like attach a camera on its tip and we can navigate and explore this environment. And also if we are discovering like an environment that is harsh for human to be there, so it's also helpful. So we can reach narrow spaces with these robots. And also, if we think about these robots, could be serve as a channel to maybe deliver water, deliver air for victims or something in earthquakes. So we can also use such applications for growing robots. So one of these robots, the growing robots, what's called vine-like robot. It is growing from inside out, as shown by this video. So it's a thin tube, a thin wall tube, and it can extend up to several meters, tens of meters, and can navigate challenging environments. And also it could be teleoperated, it could be autonomous, so according to the application itself. And we can attach a camera on the tip itself to explore, as shown here by the video itself. But one of the issues, or we have two issues actually here. Since these robots are flexible and can extend to up to several meters, the feedback control here could be challenging. Since we have couple dynamics, and also we cannot deploy some sensing points, we cannot deploy sensors on these whole length. So this is the issue. And one of the things also that is only in the vine robots or the vine growing robots is the irreversible growing process. The meaning of irreversible growing process is that this process is actually only extending process. So once we have extended the robot to a certain length, we cannot retract. So there is no retraction. This is the issue. So we need to design or to develop such a controller to consider these two challenges. So actually here, we can think about nonlinear control, since this is a nonlinear dynamics. I'm sorry. Could you mute yourself? I'm sorry. Okay, thank you. So we can think about nonlinear controllers, since we have nonlinear dynamics here in these robots. And as well, we need to consider the irreversible growing process, or the irreversible growing constraint, as you mentioned. So we think about, okay, since we have constraint and nonlinear dynamics, we can think about nonlinear model predictive control. And we will discuss in detail how this kind of control could help us in achieving the feedback control for vine-like growing robots. But actually, before diving to the control itself, we need to talk or to mention briefly the model of such robots, the vine robots. We have here the kinematics, or the forward kinematics formula or relation. We need to relate the position of the robot tip, since this robot can extend and steer. So we need to relate the position of the robot tip itself, which is XYZ in the Cartesian coordinates, with the joint space, what you call joint space or configuration space. We have three configuration space here. We have S, which is the length itself, and we have theta, which is the bending angle, and we have phi, which is, it is not a 2D, it is rotating in the 3D space, so it's called the angle of the plane. So we need to relate this three configuration variables to the three Cartesian coordinates, and directly, this is found in the literature, we can find these three formulas that relates or relating the forward kinematics. And also we need in the modeling itself what's called Jacobian, which is the derivative of this position according to the configuration space. So also we need to analytically make the derivation for the position itself with these three equations with respect to the configuration space. So now we are talking about the model predictive control. What is the model predictive control? So the model predictive control, actually, we have at a certain instant K, we have the state of the system. So we have a certain system that we can, it's a simple system, say, let's assume we have a single input, single output system. So the next state or the next instant state is a function of the current state, the current system state, and the input to the state, right? So the model predictive control will stop at a certain or at the current decision instant K, and will say, okay, in the future, if I, as a controller, output this kind of U or the control action, how the system will behave. So I am thinking about the future, in the future. So that's why it's called predictive. So based on the model, we will discuss the model right now. So I'm having the model, what will be the future or the next steps based on the current input. And if we have here that we need to do some kind of online optimization, we need to find the best values of U that will drive the future system output to the desired one. So, okay, based on this concept with the viral robot constraint, so here we are considering the constraint in the future. We don't need to be out of the sudden that we found, okay, we need to go to a certain X and Y, but unfortunately we are beyond this point. So considering this in the future, you are taking into account that we don't need to like be beyond or go beyond this point. So once we have the prediction, we can easily manage. You have a model and you have the prediction of what will be next according to your current input to the system. So that's why it will be better to behave in the future. So here, if we have the block diagram, we have the model predictive control and we have the prediction model. This is important in MPC. And we have the viral robot itself, the kinematics of the viral robot itself. So the model, we can say, okay, the X dot or the derivative of the state, which we have here 6 coordinates, the configuration, the Cartesian space and the configuration space is a function of the current space and the current input as shown here. And we need, since we have an online optimization, we need to optimize this function or this optimization function. We need to minimize the error between the desired value or the desired point, and also we need to minimize the control effort. We don't need to have a huge control effort. That's why we need to minimize these two parameters with some Q and R weighting matrices. And here we have the U, the driving control will be the Q dot, the velocity, and the error will be the reference, or sorry, the difference between the current state and the reference state. The prediction model itself, we need a simple prediction model since we have an online optimization. So we don't need to take a while or take time for doing this optimization. So we have here the discrete version using Euler discretization for the plant itself. We can say directly, we can do Euler discretization to discretize the system, and we have this prediction model. And to consider the irreversible growing process, we need to have this constraint, the S dot, which is the speed is not going to be negative, and as well, the length itself will not going to be negative value. So that's what we have here in Vine robots. Once the robot has a certain length, we cannot reduce this length. We cannot retract this length. So we did some experiments. The point stabilization experiment. We asked the robot to go to starting from an initial state X node. We asked the robot to go to a certain predefined goal point in the space. And here we have the X, Y, Z. We have the dotted lines as the reference. And here we have the solid line as the feedback or the current, the actual value. If we can see here, in the first instant, the XYZ reaches the predefined goal. And once we changed the goal of the Z value as well, it is tracking the goal. But once we need to return back here to the Z, we find that, okay, the robot will return to a certain Z, but this will be against the XY values. So according to the model itself, we can track all these values, but the issue is we need to sacrifice, if we can say, the XY values to reach a certain Z point. And also we discussed the obstacle of avoidance. We need to avoid a certain obstacle. So here we have the robot, and this dotted line is the path itself, and this is the obstacle. So easily, we just need to consider another constraint. We have the MPC can consider constraints. So we have this kind of constraint. We need the distance between the robot tip and the obstacle itself to be within a certain length. We don't need to be close enough to this obstacle. So here we have this constraint, another constraint for obstacle avoidance. And as well, we have another experiment, which is the trajectory tracking. We need to follow this trajectory, a sinusoidal wave in X and Y, and extending in the Z value. So here we can find this path or this trajectory in the Cartesian space or the 3D space where the robot is following these desired trajectory. And we need also to add another constraint, which is the workspace constraint. We don't need the robot to go to the whole workspace. We made a constraint with the X and Y, just go between -1 on Y for the X and between -0.5 meter and 0.5 meter. And here we found, even though that we have a certain reference, but to respect this constraint, the robot cannot go beyond the constraint itself for the Y axis. That's why, okay, in this region, we are following the desired trajectory, but we cannot follow this reference since we have another constraint in the Y coordinates. So also this value. So as a conclusion, we have here a nonlinear model predictive control is presented to automatically drive the vine growing robot, one of the growing robots, to a certain point in the space. And this proposed nonlinear model predictive control consider the irreversible growing process that exists in the vine robots. And as well, we have a discrete version for the prediction model, which is easy, and we don't need so much time to do the online optimization. And at the end, we tested this control or kind of control among different scenarios, the point stabilization, trajectory following, and obstacle avoidance, and we have satisfactory performance results.